Hello, folks. Today in this video, we're going to talk about optics part two. We're going to take a look this time at lenses. Let's get started. So lenses work very similar to mirrors, but the difference is that lenses use refraction rather than reflection to change the path of the light. So a thin lens is what we're going to be working with, and it's just a piece of glass that's ground so that each refracting surface is part of a sphere or a plane. So what I mean by refracting surface is that if light comes and shines at this lens, that light will bend its direction because it's going from one material into another. And so we know refraction happens anytime light enters a boundary here. Now, there's two different general types of lenses. There's convex and concave, just like mirrors. Convex lenses are converging, which is unfortunate because that's the exact opposite of what happens with mirrors. But convex lenses are converging because they cause parallel light rays to focus or converge on a single point. Then you have concave lenses. Those are diverging because they cause light rays to diverge away from a focal point. So here are a bunch of examples of different lenses. You might have seen lenses, for example, if you have glasses that look like some of these, but we're going to stick mostly with the concave and the convex simple lenses for our situations here. Now, this last point is that thin lenses have two focal points. If I show you kind of an example of a ray diagram for that, you'll notice that there's a focal point on one side and the other. The reason that being just simply because you could shine light in on either side of a lens. And like a mirror, which typically only has one reflecting surface, lenses kind of almost by definition have to be able to send light through either direction. So they'd end up having two focal points there. But we're going to be dealing with simple lenses that the focal point on each side is the same. So speaking of lenses and focal point, we can talk about the power of a lens relating to its focal length. So the power or optical power of a lens is related to the focal length using this equation. It's just power is 1 divided by that focal length. This is something that you probably actually have heard of before. Not, in any mathematical sense, though. If you want to know mathematically, the unit we use for power for lenses is diopters or inverse meters, because focal length is typically a distance measured in meters or centimeters. So you'd put it in, and that's how you'd get this. But you might have heard this going into the eye doctor and learning about your eyeglass prescription. Converging lenses tend to have a positive power, and diverging lenses tend to have a negative power. So if you know what your prescription is, for example, mine is negative, I think 1.5 in one of my eyes. That means that my eyeglasses, which I'm not wearing, are a diverging lens. So they are taking the light and making it kind of spread out a bit more than normal. Speaking of what lenses do to light, let's take a look at a ray diagram for light. Now, I'm not going to go through and do an entire example of how to draw one of these, but you'll notice that the ray diagram looks very similar to what we saw for mirrors. If you have an object here, you're still going to draw 3 rays coming off of it. The first ray is going to go parallel, hit the lens, and then go through by going through the focal length. The second ray that you're going to have, then we'll do that one in blue, is just going to go straight through the lens. Unlike the mirror, which would reflect off, it just continues on. It's the easiest ray to draw. And then lastly, our third ray will come down through the focal point and then reflect off refract parallel to that lens there. So that's what the ray diagram would look like for a lens, and you could use that, of course, to find out where the image is going to be. Now, just so you know, you could use the same equations as well. Those equations that we learned for mirrors are still in place. So 1 over f is equal to 1 over di plus 1 over do. And we know that the magnification is minus di over do, which is also hi over HO. So both of those equations are still in play for lenses as well. Now, one really neat thing you can do with lenses, though of course you can do this with mirrors, is you can combine them to produce different optical devices, making like a multiple lens or double lens system. So for example, microscopes and telescopes, any of those that have lenses in them will be using at least 2 different lenses here. Now, the way this actually works is pretty cool. I'll go ahead and move my photo here so you can see this a bit better. But the way this works is that the first lens that you have, let's say this is my object, this first lens produces an image as that light goes through it from that object. But then this next lens uses this image that's produced by the first one as its object to make a new image. And so by combining this system, you actually create something that can have optical properties that are better than you could have just with one different lens. So the model lens system works because the image projected by the first lens is used as the object for the next lens. In general, if you make like a microscope, for example, you use some objective lens, that's the one that you're putting near your sample, to make a real image, and then you're blowing that real image up and making it a virtual image through that eyepiece lens, which helps it also be upright, which is super nice as well. One big example of a multiple lens system that is important for all of us is, of course, your eye. So your eye actually has two different lenses in it. It's got the cornea and, well, the lens, which makes a lot of sense. One of the neat things, though, about your eye is because it's not made out of glass, its optical properties can be altered and changed. So you can actually focus on something by changing the focal length of your lens. You have muscles, both on the top and the bottom, surrounding that lens that actually change that focal length, which is really cool and allows you to have different optical properties depending on what kind of thing you're trying to look at, whether it's really far away or it is really close. Speaking of really far and really close, one of the most common medical issues that people have is that they might need corrective vision. They might have poor eyesight. I am included in that. I know that I am nearsighted, and what it means to be nearsighted is that I can see things far or close to me better, and things that are far away tend to be a bit fuzzier. So my eyes can do the close-up stuff, but not the far stuff. That is a condition called myopia. And so you can see a image here of what's happening in myopia here. When you have myopia, if you're looking at something far away, your lens system is essentially too good. It is focusing the light in front of your retina. So the light is focused in front of the retina. One thing to note about the lens system is that this image, by the way, is real. And if it's real, that means it would be upside down. So you actually see images upside down from where they are. Your brain actually takes the image on the back of your retina and flips it back up, which is a kind of a cool, neat feature, but that's a bit of a tangent here. So I'm nearsighted. That means my light is focused in front of my retina. So I need some type of a lens to actually like correct that, to make it so that it doesn't like converge too quickly. And so I mentioned it before that I know what my prescription is. I know it's negative. And if you have a negative prescription, you have the same thing as two. You use a diverging lens then to fix myopia. So something kind of like that. What'll happen is it'll kind of spread the light out a bit more, and then your eye, which is really good apparently at converging the light, will be able to then focus it directly on your retina. Now, as you can imagine, the opposite is true for folks who are farsighted, which is typically not something you see in younger people. That tends to be something for older people, which leads to the problem of when you have nearsightedness as a child and then you get old, then you get both of these and you need bifocals. So if you're farsighted, you have hyperopia is what it's called. Your light from your eye is focused behind your retina, which means it doesn't actually reach there. You can see here that your light won't be focused enough. Your lens system is not good enough to focus the light quick enough before it reaches your retina. So the image distance is too long. And so, of course, to fix that, you would need to make it converge quicker. And so you were going to use a converging lens to fix farsightedness or hyperopia. And that's what a converging lens would look like. It would make that light converge there. Okay, folks, that's been a bit about lenses and all the different things that kind of come along with it. Thank you guys so much for watching. Have a fantastic rest of your day.